In this video, we will discuss the development of Niels Bohr's atomic model and how it laid the foundation for the quantum revolution in chemistry. We will also explore why, without this atomic model, the chemical behavior of atoms would be inconsistent and unpredictable. But since this is an important and slightly advanced concept, I have divided this video into 4 smaller sections to make it easier to understand. In the first section, we will go over the fundamentals of Bohr's model. We will discuss the concepts of electronic orbits, energy levels, and the electronic transitions. In the second section, we will understand Max Planck's quantum theory and the idea of quantization, which Bohr used to develop his atomic model. After that, we will apply the concept of quantization to gain a deeper understanding of Bohr's model. And then finally, in the last section, we will discuss the importance of the quantized atomic model in establishing chemistry as a scientific discipline. So now that we know the plan, let's get started. In 1913, Bohr proposed his atomic model, which explained the behavior of electrons in an atom. In this model, he suggested that electrons can only revolve around the nucleus in the circular paths of fixed radii. And while revolving in these paths, they do not radiate energy. Instead, they maintain a constant energy level. He called those circular paths the stationary orbits, but for simplicity, we will just call them orbits or energy levels. The idea of electrons revolving in these orbits is easier to visualize because we can compare them to our solar system, where planets revolve around the sun in their own fixed orbits. However, understanding the concept of energy for particles as tiny as electrons can be a little bit challenging. Therefore, to make this concept easier to understand, we will use an analogy from classical physics. Let's imagine these as the 3 steps of a staircase, and there is a ball placed on the first step. Now, because this ball is at a certain height above the ground, it must have some potential energy stored inside it. And since the ball is not moving up or down, its potential energy remains constant. In the same way, when an electron revolves around the nucleus in a specific orbit, its energy also remains constant because it is at a fixed distance from the nucleus, and this distance does not change. In his atomic model, Bohr described the energy of an electron as its total energy, which includes both electrostatic potential energy and kinetic energy. Then, in his second postulate, Bohr proposed that it is possible for an electron to jump from a lower orbit to a higher orbit by absorbing a certain amount of energy from its surroundings. To understand this, let's apply some upward force on this ball and move it to the second step of this staircase. In the process of moving the ball to a higher step, we have done some work on it by applying a force. In other words, we have supplied the ball with some external energy by doing work on it, and as a result to this, the potential energy of the ball has increased. An electron also behaves in a similar way. When we provide an electron with the light of a specific wavelength or frequency, the electron absorbs this light and jumps to a higher energy orbit. The light or electromagnetic radiation that the electron absorbs is actually a form of energy. So by providing an electron with suitable electromagnetic radiation, we are essentially giving it external energy that it can absorb to jump to a higher orbit. Then Bohr also proposed that when an electron falls from a higher orbit to a lower orbit, it releases a specific amount of energy. To understand this, imagine letting this ball fall back to the first step. When you allow it to fall, the ball naturally moves downwards. During this process, its extra potential energy gets converted into kinetic energy, and once it loses this extra energy, the ball settles back on the lower step. Similarly, when an electron jumps from a lower orbit to a higher orbit, it cannot stay there forever. It eventually falls back to a lower orbit. But to return to this lower orbit, it releases a specific amount of energy. This release of energy is what allows the electron to fall back to a lower orbit. This process of electrons jumping between orbits is called electronic transition, and there are 2 types of these transitions: electronic excitation and electronic relaxation, sometimes called de-excitation. When an electron absorbs energy and jumps to a higher orbit, it is called electronic excitation. And when it releases energy and falls to a lower orbit, it is called electronic relaxation. So these were the basic postulates of Bohr's atomic model. However, to fully grasp this model, we must first understand the concept of energy quantization, a concept Bohr used as the foundation for developing his atomic model. Before Bohr, Rutherford's atomic model was used to explain the atom and its structure. But there was a major flaw in this model. According to this model, an electron would need to continuously release energy to stay in its orbit. Because of this continuous release of energy, the electron's energy would deplete over time, eventually causing it to collapse into the nucleus. In simpler terms, Rutherford's atomic model could not stabilize the atom. But to be honest, this flaw was not in Rutherford's atomic model. Instead, it was rooted in classical physics, the branch of physics Rutherford relied on to develop his atomic model. Therefore, to overcome these limitations of classical physics, another branch of physics began to emerge. This new branch, called quantum physics, was founded by Max Planck in 1900 when he proposed his quantum theory. To explain the atom more effectively, Bohr combined ideas from both branches of physics. He used classical physics to explain the movement of electron around the nucleus, but to explain the emission or absorption of energy by electron, he borrowed ideas from this new quantum theory. Therefore, in order to understand Bohr's model, we also need to start with this theory. In 1900, Max Planck introduced the idea of energy being quantized. He said that whenever a body or a particle releases or absorbs energy, it does so in the form of discrete packets. These packets of energy are called quanta, and a single packet of energy is referred to as a quantum. Then, to calculate the energy of one quantum of light of a specific frequency, we can use this formula, where E represents the energy of the quantum, H refers to Planck's constant, and V represents the frequency of the electromagnetic radiation. And by the way, this V is a Greek letter that is pronounced as nu. We will discuss this formula in more detail later in the video, but for now, let's focus on understanding the concept of quantization of energy. And to do this, we will use two analogies. So let's say you are selling these eggs, and I come to you asking for 5 eggs. You happily give me these 5 eggs. Then someone else comes along and asks for 7 eggs, and you give them exactly 7 eggs. Next, another person asks for 3 eggs, and you hand them their 3 eggs as well. Then the very next day, instead of selling these eggs individually, you package them into boxes, with each box containing 16 eggs. And you start selling the eggs this way. Your first customer comes and asks for 16 eggs, so you hand them 1 box. Then another person asks for 32 eggs, and you hand them 2 boxes. Finally, I come along and ask for 49 eggs, but you tell me that now I can only buy eggs in the form of these boxes. So I can either take 3 boxes which give me 48 eggs, or I can take 4 boxes which give me 64 eggs. You cannot sell me 3 boxes and 1 individual egg. When you are selling these eggs individually, you are selling them in a non-quantized manner. Customers could ask for any number of eggs and you could sell them easily. But when you package these eggs into boxes of 16, you started selling them in a quantized manner. And to calculate the number of eggs you can sell this way, you can use this formula, where n can be any positive integer. In other words, selling eggs in a quantized manner has put some limitations on the number of eggs you can sell, and 1 box of eggs will be called 1 quantum of eggs. So this is exactly how quantization works. But to understand the concept of quantization even better, let's use another analogy, water and ice cubes. Liquid water is the non-quantized form of water, while these ice cubes are its quantized form. Now let's start pouring this liquid water into a bottle, while measuring its mass at the same time. As I pour the water, you will see the mass increase steadily and continuously. The mass rises from 0 to 250 grams without any jumps or breaks. I can take 60 grams of water, 140 grams of water, or even 250 grams of water. There is no restriction on the amount of water I can take in this liquid form. However, if I want to take water in the form of ice cubes, I am limited by the mass of 1 ice cube, as I can only take water in the integral multiples of that mass. If the mass of this ice cube is 12 grams, and I take 1 ice cube, I get 12 grams of water. With 2 ice cubes, I get 24 grams of water. With 3 ice cubes, I get 36 grams of water, and so on. It is impossible for me to take 49 grams or 61 grams of water using these ice cubes because they are the quantized form of water. So I can either take 48 grams of water in the form of 4 ice cubes or 60 grams of water in the form of 5 ice cubes. And this is why we can say that the liquid state of water is its non-quantized form, because we can take any amount of water in this form. But ice cubes, on the other hand, are the quantized form of this water, because we can only take water in specific quantities using them. And 1 ice cube will be called 1 quantum of water. These same concepts of eggs and water also apply to the quantization of energy. Using this formula, we can calculate the amount of energy in 1 quantum of any electromagnetic radiation using its frequency. However, if we don't have the frequency of that electromagnetic radiation, we can modify this equation using the relationship between frequency and wavelength. We can rearrange this equation to get the value of frequency, which we can then plug into our first equation. And now, We are all set to calculate the amount of energy in one quantum of any electromagnetic radiation using either its frequency or wavelength. For example, let's say we are asked to calculate the energy of one quantum of this red light. To do this, we first need to convert this wavelength into meters. Then, we will use the second equation and plug in the values of wavelength, speed of light, and Planck's constant. After solving this equation, we will obtain the energy of one quantum of this electromagnetic radiation. Now, even though the SI unit of energy is joule, however, at the atomic level, we use another unit called the electron volt. This is because, as you can see, at the atomic level, we deal with much smaller quantities. So using a smaller unit like electron volt is much more convenient. To convert this energy into electron volt, we can simply use this conversion factor. And now, whenever a body or a particle releases or absorbs energy in the form of this red light, it can only do so in the form of energy packets which contain exactly 1.77 electron volts of energy. To determine the amount of this quantized energy that can be absorbed or released, we can use this formula, where n can be any positive integer. Just like those boxes of eggs or ice cubes, a particle can either exchange 5.31 electron volts of energy in the form of 3 quanta, or it can exchange 7.08 electron volts of energy in the form of 4 quanta. But it is impossible for a particle to exchange 5.12 electron volts of energy or 7.19 electron volts of energy, because that would go against the principles of quantum theory. Another important point to remember is that each type of electromagnetic radiation has a different amount of energy in its quanta, and this amount depends on the frequency or wavelength of that electromagnetic radiation. So that was Max Planck's quantum theory, which Bohr used to develop his atomic model. 5 years later, Einstein expanded on this idea, proposing that light behaves like a particle instead of a wave. These light particles were later called photons. However, over time, scientists concluded that light actually behaves as both a particle and a wave. In some situations, it acts like a particle, and in others, it behaves like a wave. This was a revolutionary idea because it helped explain many scientific phenomena, but this is a topic for another discussion. For now, let's return to Bohr's atomic model and understand it using the concepts of quantum theory. So in his first postulate, Bohr proposed that when an electron revolves around the nucleus in an orbit, it does not radiate energy. Instead, its energy remains constant. Since electrons have mass and revolve around the nucleus with an angular velocity, they also possess angular momentum. Bohr proposed that this angular momentum of electrons is not random and can only have specific quantized values. Based on this, he further suggested that electrons don't just revolve in any random orbit. Instead, these orbits must also have specific quantized radii, which correspond to the angular momentum of electrons revolving in them. To calculate the radius of orbits for all hydrogen-like atoms, he derived this equation, where n represents the orbit number, which was later called the principal quantum number. This principal quantum number can only take positive integer values, such as 1, 2, 3, 4, 5, and so on. For example, these are the principal quantum numbers and the radii of the first 3 orbits of a hydrogen atom. Any electron in these orbits can only revolve at these specific radii. It is impossible for an electron to revolve in any orbit between the first and second one, or between the second and the third one. This is because such orbits would violate the principles of quantization. Just as we can only sell specific quantities of eggs in the form of boxes, or take specific amounts of water in the form of ice cubes, the quantization of orbits means that electrons can now only revolve around the nucleus in orbits of specific radii. All the orbits in an atom where electrons can revolve are called allowed orbits, or allowed energy levels. Orbits other than these are called forbidden orbits, or forbidden energy levels. Because of these orbits of quantized radii, electrons in these orbits will also have quantized energy, as they are now only able to revolve at certain fixed distances from the nucleus. And as long as an electron stays in its orbit, it maintains that energy. Bohr also derived a formula to calculate the energy of these allowed orbits. In this formula, RH represents Rydberg's constant for hydrogen, and n is the principal quantum number of the orbit for which we want to calculate the energy. Using this formula, we can calculate the energy for these 5 allowed orbits of hydrogen atom. And as we did earlier, we can also convert this energy into electron volts for our convenience. Now as you can see, all of these orbits in this atom have a specific value of energy. Therefore, electrons in this atom cannot occupy any energy level other than these allowed ones. For example, if an electron is in the first orbit, its energy will always be negative 13.6 electron volts. It cannot have negative 13.7 electron volts or negative 13.5 electron volts. This is why Bohr used Max Planck's quantum theory to develop his atomic model, to quantize these orbits and their energies. Because without quantized orbits, an atom would not be able to stabilize itself. Then the negative sign with the energy value indicates that this electron is bound to the nucleus. The more negative energy an electron has, the more strongly it is bound to the nucleus, and the more stable it will be. The orbit closest to the nucleus has the most negative energy. As a result, electrons in this orbit are the most strongly bound, and therefore the most stable. However, as an electron moves further away from the nucleus, its energy becomes less negative, until it eventually escapes the attractive field of nucleus. At this point, the nucleus can no longer hold the electron, and it becomes a free electron. This point in space where the electron no longer feels any attraction from the nucleus is called the zero point, and this orbit will be called an unbound or escape orbit. Below the zero point, the orbits gradually have increasingly negative energy, with the first orbit having the most negative energy. In his next postulates, Bohr had also proposed that electrons can change their orbits through a process called electronic transition, and this process involves emission or absorption of energy. When an electron jumps from a lower orbit to a higher orbit, it absorbs energy, and when it falls back to a lower orbit, it releases energy in the process. To calculate the amount of energy involved in these electronic transitions, we can use this equation. In this equation, delta E represents the energy involved in an electronic transition, EF is the final energy of electron, and EI is the initial energy of electron. The values of EF and EI can be determined using this equation. Here, an F is the principal quantum number of the final orbit, and an I is the principal quantum number of the initial orbit. After plugging the values of EF and EI into the first equation and rearranging it, we arrive at this final equation. With this equation, we can calculate the amount of energy involved in any electronic transition. Positive value of energy indicates the absorption of energy during the transition, while a negative value indicates the release of energy. For instance, let's suppose we are asked to determine the energy change that occurs when an electron jumps from the first orbit to the second orbit. We can easily calculate this energy change using this equation. Since the electron is jumping from the first orbit, this will be its initial orbit, and the second orbit will become its final orbit. This is the value of Rydberg's constant, and after solving this equation, we obtain the energy change involved in this electronic transition. For convenience, we can also convert this energy into electron volt. Now because this energy is positive, it means the electron will absorb 10.2 electron volts of energy when it jumps from the first orbit to the second orbit. Most of the time, this energy is released or absorbed in the form of electromagnetic radiation. Therefore, in addition to calculating the energy, we can also calculate the frequency and wavelength of the electromagnetic radiation involved in any electronic transition. To calculate frequency of that electromagnetic radiation, we can use Max Planck's equation of quantum theory along with this equation. Since both of these equations share a common left side, we can equate them to derive this new equation. However, to calculate the wavelength of that electromagnetic radiation, we need to modify this equation using the wavelength frequency relationship. And now, by rearranging these equations, we derive these formulas to calculate the frequency or wavelength of the electromagnetic radiation released or absorbed during an electronic transition. For example, if we want to determine the frequency of electromagnetic radiation that can excite an electron from first orbit to third orbit, we can use this equation. The first orbit is the initial orbit, and the third orbit is the final orbit. After plugging in the values of Rydberg's constant and Planck's constant into our equation and solving it, we get the frequency of that electromagnetic radiation, which is 2.92 times 10 raised to the power 15 cycles per second, or 2.92 times 10 raised to the power 15 Hz. And now, to excite an electron from the first orbit to the third orbit, we must provide it with a photon of electromagnetic radiation that has a frequency of 2.92 times 10 to the power 15 Hz. So these were the basic postulates of Bohr's model, which explained the atomic structure in a greater detail. Yet, despite successfully explaining various atomic phenomena, Bohr's model had some serious limitations as well. One major drawback that limited its applicability was that it could only explain single electron atoms. When applied to complex multi-electron atoms, the model failed miserably. Another issue was its assumption that electrons move around the nucleus in two-dimensional circular orbits. Later studies revealed that instead of these simple two-dimensional circular orbits, electrons occupy more complex three-dimensional regions called orbitals. Beyond these, the model had several other shortcomings as well. But even with all of its limitations, It was the first model that successfully incorporated quantum principles into atomic theory, which was a turning point in the history of science. It marked the beginning of a new era where the principles of quantum mechanics began to integrate into our understanding of the atom. Therefore, to appreciate this atomic model even more, let's compare it with the hypothetical non-quantized atom. The first difference between a quantized atom and a hypothetical non-quantized atom is the distribution of electrons. Non-quantized atoms would not follow Max Planck's quantum theory. Therefore, their electrons would revolve in any random orbit they like. This is because there would be no restrictions on the energy or the size of their orbits. Due to this random electronic distribution, no two atoms of an element would share the same electronic configuration. This random electronic configuration would, in turn, lead to completely unpredictable and inconsistent chemical behavior of atoms. Because the chemical behavior of atoms depend on these electronic arrangements, chemical reactions would become inconsistent, and every time you perform a chemical reaction, you would get a different outcome each time. On the other hand, because quantized atoms follow quantum theory, their electrons can only occupy certain allowed orbits. Due to this limited number of allowed orbits or energy levels, the electronic configuration of these atoms becomes consistent. This consistent electronic configuration in atoms gives us predictability and consistency in chemical reactions. And as a result, we can predict the outcome of a chemical reaction even before performing it. In addition, the periodic properties of elements such as ionization energy, electron affinity, and electronegativity also help us predict the chemical behavior of atoms. All of these properties depend on the quantized nature of the atom. Without quantized nature, atoms would lose their electronic configuration, disrupting the predictable trends in these properties. Therefore, for atoms to be stable, maintain a consistent electronic configuration, and exhibit predictable chemical behavior, they must be quantized. Without this quantized nature, chemical reactions and properties of matter would become unpredictable, and as a result, chemistry as a subject would not exist. Then, another important outcome of a quantized atom is the quantized electronic transition. Quantized electronic transitions means that electrons can only transition into allowed energy levels or orbits, and in these transitions, they will only emit or absorb the electromagnetic radiations of distinct wavelengths. It is only due to this behavior of atoms that we are able to see colors in our world. Because if atoms were non-quantized, they would not emit or release light in distinct wavelengths, and our world would become only black and white. It is also due to the fact that the atoms emit and absorb electromagnetic radiations of distinct wavelengths. We are able to analyze and identify matter using a special technique called spectroscopy. So these were some important benefits of Bohr's quantized atomic model, which gave chemistry a new direction by incorporating quantum theory into the atom. However, to address the limitations of this model, scientists developed a new atomic model, one that relied entirely on quantum mechanics to explain atomic structure. This model was developed through a series of groundbreaking works, including wave-particle duality, Schrödinger's wave mechanics, and the uncertainty principle. Together, these advancements provided a more comprehensive understanding of atomic structure. Therefore, to fully grasp the modern concept of the atom, we must also study the quantum mechanical atomic model. And that is exactly what we will do in the next video. In the next video, we will break down the basics of quantum mechanical atomic model without going into complex mathematical explanations. So see you in the next video. Until then, peace.